Welcome to your Algebra 2 lesson for 10.1, Applying the Counting Principle and Permutations. All right, it seems like counting should be a really easy thing, and it is if you can see the number of objects in front of you, and like when you were a little kid, go 1, 2, 3, 4. I've got 4 bean bags here with me. But what if you can't see everything that you need to count? We need some techniques to help us with that. One technique is to use a tree diagram. Okay, a sporting goods store offers 3 types of snowboards: all mountain, freestyle, and carving, and 2 types of boots, soft and hybrid. How many choices does the store offer for snowboarding equipment? Well, one way to do this is to create a tree diagram and then count the number of branches once you get through all your options. Okay, so you start off and you list all possibilities for your first choice you need to make. So I've got 3 options for that: all mountain, freestyle, and carving. And then, so we've picked our board. Now we need to pick our boot. So at this point we need to decide if we want soft or hybrid. And you have that soft or hybrid choice for each one of the boards. Doesn't matter which board you have, you're not restricted on which boots you can get. Then you've created all possible combinations, okay, all possible pairings. So we've got all mountain board with soft boots, all mountain board with hybrid boots, and so on. And you can just count. There's 1, 2, 3, 4, 5, 6 possible choices. Okay. Now, we can actually do that counting without looking at all the possible choices. Sometimes this is really helpful, but what if we had 100 different choices for the first one and 27 choices for the second one? We would have a huge tree diagram, so it wouldn't be very efficient. So we use the fundamental counting principle, which basically says if you've got 2 events and there's m ways to choose the first one and n ways to choose the second one, you just multiply m times n. If you have 3 or more events, you just keep on multiplying. So if we had m options for our first choice, n for the second, p for the third, we would do m times n times p, and so on. All right, so let's look at that. You are framing a picture. The frames are available in 12 different styles. Each style is available in 55 different colors. You also want a blue matte board, which is available in 11 different shades of blue. How many different ways can you frame the picture? Well, we certainly wouldn't want to make a tree diagram with 12 branches, followed by 55 branches off of each of the 12 branches. So we're going to use the fundamental counting principle to solve this. So we do 12 times 55 times 11. You just do the number of options for the frames, frame colors, and shades of blue for your mat, and you get 7,260 different ways you could do your framing. All right. For license plates, the standard configuration for a Texas license plate is 1 letter followed by 2 digits followed by 3 letters. How many different license plates are possible if the letters and digits can be repeated? So as in the example up here, you can see that A is repeated. It wouldn't have to be repeated every time, but just that each letter can be repeated, and then each of the 10 digits from 0 to 9, you could repeat them. It's, in other words, once one is used, it's still available for use again. And then we're going to well, what happens if they can't be repeated? That once you use A, it's done. And once you use 9, it's done. You can't use it again. All right, for solution A, the number of plates would be 26 for the first letter, 10 times 10 for each of the digits. Remember, it's 0 through 9, so 0 makes your 10th digit, times 3 more letters, so 26 times 26 times 26, and we get 45,697,600. But what if we don't allow repeats? Well, you'd have 26 letters to choose from on your first choice, and you'd have the 10 digits to choose from on your first choice of digits. But whatever digit you chose here is not available for your second digit, so you're going to multiply by 9. And then when we do our next letters, you still have 25 available. Every one of them except the one chosen over here. So it would be 25 and then 24 and 23. And so we get 32,292,000. So it reduces our number of options. Still a lot, though. All right, so in this chapter, your problems to try on your own are going to be called guided practice, and they are going to be embedded within the lesson. So go ahead and pause now and try this guided practice 1 and 2 there, and then we will go over these in class just like we normally do for problems to try on your own. But go ahead and pause the video. These will be related to examples 1, 2, and 3, and then we'll go over them in class. Okay, you need to learn a new symbol. It's called factorial. It is an exclamation mark. So this is read n factorial, and it's equal to n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. We have to define 0 factorial, and it's equal to 1. So if you put this in your calculator, if you do 4 exclamation mark, go ahead, grab your CAS and do it, and then press enter, it's going to give you 24. That's really cool. It's the 4 times 3 times 2 times 1. Okay, a permutation is an ordering of n objects. Okay, the 6 permutations of the letter A, B, and C are A, B, C. Okay, and then we're going to change the order and it gives us a new permutation. Okay, let's do ACB, BAC, BCA, CAB, and CBA. So with permutations, the order of the individual objects matter. It's not just the collection that you have an A, a B, and a C, it's which order they occur in. So the number of permutations of n distinct objects is n factorial. So there's 3 distinct objects, so the number of permutations for A, B, and C are 3 factorial, which is 3 times 2 times 1, or 6. Okay. So 10 teams are competing in the final round of the Olympic 4-person bobsledding competition. In how many different ways can the bobsledding teams finish the competition? Assume that there's no ties. So then we're going to see how many different ways can 3 of the bobsledding teams finish first, second, or third to win the gold, silver, or bronze medals. Okay, so for our first one, we've got 10 factorial equals 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that is 3,628,800. And again, you can multiply it all out like that, but there is an exclamation mark on your calculator, and you can just do 10 factorial, 10 exclamation mark, enter, and it's going to give you your answer. For part B, we're just looking at three places. So there's 10 different teams that can come in first place, 9 different teams then that can come in second place, because you can't come in first and second place at the same time. Okay, so once we've got our second place winner, there's 8 teams remaining that can come in third. So 10 times 9 times 8. Okay, so now we have a guided practice for this one, and so go ahead and do that. All right, welcome back. Now we're going to do the permutation of n objects taken r at a time. In other words, we're not going to select all of our objects, but only a certain number. And so the way that's read is n permute r, and that is equal to n factorial over n minus r factorial. And there is a way to just enter this into the calculator directly, and we'll go over that in class. If you want to play around with your calculator and find it, that's great. If not, just practice using that factorial button, or work them out as I show you in the video. But it's going to be really important that you attend the next class, because I'm going to show you some cool stuff on your calculator. All right, we're going to find permutations of n objects taken r at a time, and our situation here is you are burning a demo CD for your band. Your band has 12 songs stored on your computer. However, you want to put only 4 songs on the demo CD. And how many orders can you burn 4 of the 12 songs onto the CD? Okay, so for this, you're doing 12 permute 4, and that is equal to n factorial over n minus r factorial. So in this case, 12 factorial over 12 minus 4 factorial. N is always going to be at least as large as r. So if there's a number that's smaller and a number that's larger, n is the larger number and r is the smaller number. So we have 12 factorial over 8 factorial, and so you can just put that into your calculator. 12 factorial is 479,001,600 over 8 factorial, which is 40,320, and that comes out to be 11,800. All right, sometimes we have permutations with repetition. The number of distinguishable permutations of n objects where one object is repeated S1 times, another is repeated S2 times, and so on, is n factorial over the product of each of those little s's factorial. So S1 factorial times S2 factorial up to SK factorial. So that's definitely something that's easier to see with an example. So let's look at a couple of examples here. We're going to find the number of distinguishable permutations of the letters in MI, AMI in Miami, and then Tallahassee. So Miami has repeats for M and I. Tallahassee has a whole bunch of repeats. So let's look at what we do. So for Miami, it's going to be the total number of letters factorial. So there's 5 letters, so 5 factorial. And then anything with a repeat, we are going to consider in the denominator. So there's 2 m's, so we have a 2 factorial for our 2 m's. And then there's 2 i's, so we have a 2 factorial for the i's. And what that does is it takes out the different orderings of the m's and the i's. Okay, because we can't distinguish between one capital M and another. So we've got to reduce our total number of permutations just for 5 letters for those repeated permutations. So 5 factorial is 120. 2 factorial is 2 times 1, so it's just 2 times 2. And so 120 divided by 4 is 30. So there's 30 distinguishable permutations of the letters in Miami. All right, so let's do Tallahassee. There are 11 letters in Tallahassee, so we have 11 factorials. Let's see. The A is repeated 3 times, the L is repeated 2 times, the S is repeated 2 times, and the E is repeated 2 times. So we have 3 factorial for the A, 2 factorial, 2 factorial, 2 factorial for the other repeated letters. So 11 factorial is 39,916,800. And then the product of our factorials on the bottom here, we're going to have 6 times 2 times 2 times 2. And so that is 6 times 8, which is 48. And when we do our division, we get 831,600 different orderings of the letters in Tallahassee where we can distinguish between them. All right, so now you just need to do the guided practice that goes with example 6. You want to find the number of distinguishable permutations of the letters in the word mall, and then you are done. All right, awesome. Make sure you've tried all of the guided practice, the problems to try on your own, and we will go over those in class. Come see me if you need any extra help before the next class. Have a great day.